Hello everyone, I'm Prajval Shastri and I will try and explain why I, like so many all across the planet, are so excited about what the James Webb Telescope team just did a few days ago. What is its significance and what it holds for the future. So, as you perhaps saw on TV a few days ago, the James Webb Telescope team presented a few images of the cosmos, images that had been held a tight secret until the President of the United States released them to the world. You'd have also seen that along with President Joe Biden were present Vice President Kamala Harris, along with some of the team members of the telescope project. She is also the president of the Space Council of the United States and spoke very evocatively about the enterprise. So why this big deal? It was a best effort on the part of everyone involved to present as spectacularly as possible the very first and I should say preliminary insights of what has been an effort that has lasted over 2 decades, involves thousands of scientists, engineers, and support people, and cost roughly $10 billion. So, if we compare the Indian scientific research situation, India had a clear science policy since as early as 1958 that committed public expenditure to science based on a clear vision that fruits of science and thereby scientific thinking for everyone is a thing of the future, which was taken quite for granted. On the other hand, even in the best of times in the US, scientists have always had to strongly justify public expenditure for science. The Hubble Space Telescope, along its journey that continues even today, has come to excel in this by not only enabling scientists from the world over to access the telescope to explore their new ideas about the cosmos, but also specifically designing exposures of the sky to create a legacy of images of extraordinary beauty that are indelible in the public imagination, which brought very new scientific, new angles on our understanding of the cosmos and our place as humans in the universe. The James Webb Telescope, which is a complementary mission to the Hubble Space Telescope, has clearly built upon these lessons at the word go itself, creating, or rather starting, an extraordinary heritage. So let's start at the beginning. What is the James Webb Telescope? It's a telescope that can see light that the human eyes cannot see, namely infrared light, that has been launched into space much further from us than even the moon in order to study the cosmos. It complements the famous Hubble Space Telescope, which is still up there exploring the cosmos. So in what ways is this different, and what's behind this sort of feeling that it's going to take us many leaps forward in our understanding? To begin, let's look at these pictures from the Hubble. So this is a picture of a tiny bit of sky where we have known for a while that there is a large cloud of gas and dust, and stars like our own sun are forming there. On the left is a picture that Hubble took in visible light, and you can see stars in these portions, but not in these portions. And the same bit of sky photographed in the infrared on the right is shown. So the colors of light, so to speak, are quantitatively characterized by the frequency of the electromagnetic wave, similar to the frequency of sound. So how fast the electromagnetic wave the electromagnetic field changes, if you like, or the wavelength. And they are complementary. So higher frequency means lower wavelength. So the infrared light has lower frequency than visible light, but longer wavelength than visible light. So of the order of 1,000th of a millimeter, which we call micrometer or micron. So this infrared picture by Hubble on the right shows stars inside these clouds of gas and dust. So that's the thing. You can peer into a cloud of gas and dust with infrared light. So clearly, if we want to learn the detailed physics about how stars form in what have been referred to as stellar nurseries, infrared light is the way to go. But that is for our own Milky Way and a few nearby galaxies. So there's a side point here, and that is that I said that humans cannot see infrared light. So then what does it mean to show you a picture with orange and lavender and other colors, saying that it's an infrared picture? So the truth is that these colors are not real colors. They only indicate how much infrared light is coming. And they're just the best way, the most beautiful way of rendering what the infrared sensors pick up. So the choice of colors is completely arbitrary and fanciful, the choice of the renderer. So here are some pictures that may make this clearer. So here's a picture of a cat, and here's an infrared picture of the cat. And now there's one other thing about the infrared. Even though the human eyes cannot see infrared, and by the way, the radiation used in the TV remotes, etc., is infrared light. So even though we cannot see it with our eyes, we can feel it as warmth, because warm things, including our own body, and certainly an iron that you use to iron clothes or a burning fire, emit infrared. So these false colors in the picture tell us that there is less infrared light from the nose of the cat, which we know is cold, and more infrared light from the eyes and the ears, etc. And this is to show that the choice of colors is totally arbitrary. So this is the same picture of the cat, and the colors have meaning actually only when there is a key that tells us what color means what intensity. And here's a warm hand, so more infrared light from the hand. The shirt emits less infrared light, and the worm is even cooler, so the least amount of infrared. And what better illustrates false colors than this beautiful image taken by the James Webb Telescope of a dying star like our own sun. So here the false colors represent both different frequencies or subcolors, if you like, within the infrared, and the intensity of the color represents the intensity of light. So these are taken with very different cameras on the Webb telescope. The one on the right is sensitive to longer wavelengths or lower frequencies than the one on the left, all in the infrared. So as you can imagine, a quantitative comparison of the two can tell us a lot about the physics of what's going on. But on the topic of false colors, do notice that the color cyan, the false color cyan, has been used to represent very different subcolors in these two pictures. So on the left, it represents the subcolor at about 1.8 microns, whereas in the picture on the right, it has been used to represent about 11 microns. So all the images from the James Webb Telescope are rendered in false color. And that brings me to the other beautiful image that the Webb Consortium released, metaphorically called the cosmic cliffs in the Carina Nebula. And you can see that the renderer has made a very deliberate, poetic choice of false colors to render the data. And it's, of course, nothing like cliffs as we know them on Earth, but there's a huge amount of physics in there, even visually. So this is a stellar nursery, as we have seen with the earlier Hubble picture. A lot of stars have just formed, so they're hot, and they sublimate away all the dust and blast away the clouds of gas. But the influence ends in this very sharp boundary, on this side of which the cold gas and dust exist, and so stars are forming and will form, which we can see because infrared light can penetrate the clouds. And we see much, much more than what the Hubble could see, partly because of the much larger light collecting area of the Webb telescope, 6 times that of the Hubble. By the way, this kind of mirror that is a jointed one of hexagonal mirror segments with gaps of about 4 millimeters between them has been used in several telescopes on Earth before, but is a first timer for a space telescope. And this picture illustrates another difference with the Hubble, which is the very wide range of infrared light that can be detected. So the same Carina gas nebula was also photographed at longer infrared wavelengths, and the lower picture is a so-called composite of all the infrared colors added up and shown in false color. And there is an enormous amount of quantitative work that can be done with this. I have circled a couple of regions that you can look at later. The differences are very subtle visually, but can tell us many things about the temperatures, the compositions, and what's going on. And that brings me to the business of the tennis court-sized sun shield of the Webb telescope. So, since infrared light comes from warm things, and since the Webb telescope is trying to detect such light from extraordinarily faintly shining things in the cosmos, it is important that the telescope itself be cold so that its sensors don't get swamped by the infrared light from the warmth of the telescope itself. So the solution to this problem is two-pronged. First, have this amazing sun shield, tennis court sized it is indeed. And second, send the telescope out far, far away. So the telescope has been launched to a very special place with a quaint name, Lagrange 2, after a mathematician called Lagrange. It was apparently, in fact, discovered by his guru, Euler, but never mind that for now. Of gravity due to the sun and the earth, and how the telescope is made to move, creates a region of equilibrium where forces are in balance. So such a place is always outside of the orbiting system. So you have the sun, the earth, and the telescope. And it is made to move so that it's always moving along the earth in its orbit around the sun. So the sun is always beyond and behind the earth for the telescope, which is good. Because it's a region of equilibrium, if the telescope goes a bit astray, it will only require a little nudge now and then to bring it back. So with the fuel that the telescope has in store, this correction can go on for the next 20 years. It's a matter of detail that within that place, the telescope actually is in a little orbit of a few tens of thousands of kilometers around L2. Now, the Webb telescope was conceived over 20 years ago, but since its original scientific quest was articulated, something really interesting had started to happen independently. Planets started to be discovered around stars other than our sun. Within a few years, it became very clear that the Webb telescope, with its enormous sensitivity in the infrared, would be very well poised to investigate the atmospheres of such planets. So to dive into that a bit, let us first look at this very, very powerful astrophysical tool called spectroscopy. So we've all seen rainbows in the sky, and we know that water droplets spread light into rainbow colors, just like a prism does in the laboratory, and so on. These colors are all of different frequencies, of course, with red the lowest frequency or longest wavelength, and violet the highest frequency or shortest wavelength. Now, what happens if this light is spread out much more, much more, which is hard to do with a prism, but can be done with things called gratings, which are like the surface of a compact disc or CD. What happens is on top of a sort of rainbow, we start to see a very large amount of light coming at very specific frequencies, like this. And we call them emission lines. And depending on how hot the source of light is and what's in front of it, etc., we might also see the opposite. That is, on top of the rainbow, almost no light coming at all from certain frequencies. And you can actually see this if you try and look at sunlight reflected off a CD. It's a very beautiful toy that can be constructed, that our famous toy designer Arvind Gupta had designed. So why do we see these lines, whether bright or dark? Because the atoms or even molecules in the gas of whatever is emitting the light or absorbing the light get excited only by very definite amounts when they are energized, either by light or by some other means. So they get excited by absorbing a very specific amount of energy from the light shining on them, which is the same thing as saying they absorb a very specific frequency of the light. So that's what causes those dark lines, because they remove that light from the original source. Or they get excited by being heated or something, and then they can't just sit there for long, so they get de-excited to a lower level of energy, but again emit a very specific frequency of light, the emission lines. So this is a quantum physical effect which we don't notice with our bare eyes, but we can see it with the help of something like a CD. So what specific frequency of light? That depends on which element it is. So each element has its own signature set of specific frequencies, or lines as we call them, like a fingerprint. And the temperature will determine which subset of those lines are seen. Now, a gas cloud will have many elements like hydrogen, oxygen, etc. So what we see is a combination of all these signatures. However, we know the exact frequencies of these lines because we've studied them in the laboratory. And the amazing thing is that wherever these gas clouds are, whether in our laboratory or in the dim reaches of the cosmos, the element emits the same frequency. So why is this such a powerful tool for astrophysicists? Firstly, it tells us what elements are there, so the composition. Secondly, it tells us the temperatures. And the third reason, it's really cool. So if the atom or the star that the atom is in, or the gas cloud it is in, is moving towards or away from us, the frequency of those very specific lines are Doppler shifted to higher or lower frequencies. Just like sound is shifted to higher or lower pitch when the source of sound moves towards or away from us, which you're very familiar with. And the fourth reason is even more cool, that the expansion of the universe stretches the light of these lines. So the further they're coming from in the universe, the more the stretching. And so by measuring this stretching or increase in wavelength or lowering of frequency, we can measure how far they are. So now back to planets around other stars, or exoplanets as they're called. They were predicted a very long time ago by Giordano Bruno, and now we know about 5,000. That's a story in itself for another day by someone else. Now, these planets may have atmospheres, and if they do, the molecules in the atmosphere will emit and absorb at specific frequencies, and a lot of these frequencies are in the infrared. So, the study of exoplanets entered the Webb telescope mandate, and not surprisingly, it began to loom extremely large. And one of the results revealed at the presidential event was this spectrum of the atmosphere of an exoplanet, revealing the signature of water molecules. So the planet called WASP 96b is a gas giant around a sun-like star. It was not discovered by Webb. I don't think it takes away anything from the telescope's fantastic result to point out that the discovery had happened earlier by a consortium of robotic telescopes called the Wide Angle Search for Planets, or WASP, by the technique where they search for light from the parent star being reduced for a short time as the planet passes between the star and us in orbit. This reduction will, of course, happen periodically. So the thing is, when the planet is between us and the parent star, some of the light from the star would pass through the atmosphere of the planet, if it has one. And in this case, it does. And here is the spectrum that Webb got of that happening. So it looks different from the spectra I showed earlier, only because instead of rendering it as a false color picture, a cross-section of the data has been taken and rendered as a graph. And Webb was able to measure the fingerprints of the water molecule of the atmosphere of planet WASP 96b. The sticks indicate the uncertainties of the measurements, and the blue curve indicates the result of modeling. In other words, it reflects our present understanding of how and what is there in the atmosphere. And the mismatch between the blue curve and the data shown by the sticks is an indicator of what is yet to be learned. Okay, so the next image that President Biden released was of the Stefan's Quintet of Galaxies. Now, this is a very, very well-studied group of 5 galaxies in the Pegasus constellation area of the sky, a discovery credited to Stefan in the 19th century. And when we say group of galaxies, we mean that there are a bunch of galaxies, like our Milky Way, physically close by to each other and therefore strongly influencing each other gravitationally. So it so happens that this galaxy is proximal to the group only in the sky, but is actually much closer to us and is in the foreground of the other 4. So it's not physically part of that group, and the 4 are this, 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 and this. So there's a lot going on here. I particularly want to point out that each of these images has, apart from the primary object of interest, so many galaxies and nebulae and stars in the background, foreground, with so much serendipitous science embedded in there, waiting to be discovered. So the 4 galaxies of the Stefan's Quintet are interacting, which means their gravity is throwing their orbits of the stars out of whack, compressing some of the gas, which leads to more star formation and so on, as is also seen in this longer wavelength image, which the Webb took, and it shows it more clearly. And while all these galaxies are expected to have giant black holes, that is, black holes more than 1 million times the mass of our sun, in their middles, one of them is a munching black hole, which means it's in the process of swallowing any material that approaches very close to it, and therefore it's spewing out a lot of energy, which then excites and accelerates the gas around, which can be seen in these images. So these images use a very special but very well-established technique. They are actually a collection of images at every frequency observed. Or said another way, they are a collection of spectra of every piece of the galaxy. They are referred to as a data cube, so 2 axes on the sky and 1 axis along frequency or wavelength. And they're made with an instrument with the most boring name of integral field unit. But they're really fantastic because if you have a galaxy, you have the image of that galaxy at every frequency, thanks to this instrument, and every piece of the galaxy has a spectrum. And so for every piece, You know the composition, the excitation, and the speeds the gas moving towards or away from us. And so that brings me to the very first image that President Biden revealed. A tiny, tiny bit of sky, about a 20th the size of the moon in the sky, which reveals thousands of galaxies. So in many ways, this is a repeat performance of the images that the Hubble gave us starting about 25 years ago, showing 3,000 galaxies in a bit of sky, a third of the size of the moon, then later 10,000 galaxies in a bit of sky, a tenth of the size of the moon, and never looking back then on. So in this image also, virtually every dot and smudge is a galaxy, except these cross-shaped things, which are stars in our own Milky Way, which are in the foreground. So very sharp but very bright points of light in the sky, like stars, give rise to these spikes, which are instrumental artifacts. And there may be 4 spikes or 6 spikes, depending on the structure of the supports that have to be there to support either a camera at the focus of a telescope or a second mirror at that focus, as in the James Webb case. So here there is also contribution to those artifacts by the hexagonal edges of the mirror segments. So stars have 6 spikes in Webb images, 4 spikes in Hubble images, and so on. So apart from these foreground stars, you see a cluster of galaxies, which is a very large gravitationally interacting bunch of galaxies influencing each other, whose light left those galaxies about 5 billion years ago, sort of similar to when the solar system originated. But they also constitute an enormous amount of mass. So as Einstein predicted and Eddington verified over a century ago, this enormous mass bends the light from the galaxies behind it. And these galaxies therefore appear to stretch kind of around this central mass. So here is the Hubble image of the same region for comparison. And you can also compare the artifacts and the images of stars. 2 of these stretched out structures have been confirmed by Webb using spectroscopy to be gravitational mirror images of the same galaxy rather than 2 different galaxies. None of this is surprising or entirely new, but what is exciting is that the Webb telescope has shown that it will be able to realize one of its big goals, which is to look for the earliest shining objects ever. How can we look at the earliest objects? It's because even though our everyday experience makes us feel that light travels instantaneously, light does take time to travel. So I've heard that Grace Hopper, the mathematician and pioneer computer programmer, used to carry around 30 centimeter long cables to point out that light would take 1 nanosecond to travel across them. That is a billionth of a second to travel across them. So it takes light more than a second to reach us from the moon, about 8 minutes to reach us from the sun, and about 4.5 years to reach us from the next nearest star. Which means that we can never know what happened there now, but only what happened on the moon over a second ago, or in the sun 8 minutes ago, or in the next nearest star 4.5 years ago, etc. So we're always out of date. And this may sound like a bad thing, but it really isn't, because it means that by looking further and further away, we're really peering back in time and learning history. And that's the thing with the Webb telescope. It has been able to see light that left these distant galaxies 13 billion years ago. Of course, the universe is expanding, meaning its space-time is stretching, so the light that we are seeing as infrared after this stretching was emitted as ultraviolet light by stars that were forming around 13 billion years ago. And that, in the larger cosmic scheme of things, is pretty close to when the universe began. And because we think that the universe is sort of the same everywhere, looking at these very first objects shining is equivalent to looking at our own neck of the woods way back, close to when the universe began. So therefore, at our own history, really. So Webb hasn't yet seen the earliest shining galaxy ever, but even the preliminary images show that it is pretty close. So this telescope, as the hashtag, that was a lovely play on words, states, unfolded itself to now unfold the universe. It's a really big telescope and had to be big, with a big sun shield and big solar panels in order to achieve its scientific goals. So such a big telescope would not fit into a rocket that was to be used for launch. So it was really rocket science to have to fold up everything just to fit into the rocket, then launch it, which was on Christmas Day last year, and then unfold things one by one. First the solar panels, then the transmitter, then the sun shield, and then the telescope mirror itself. Even though the first images were released by the American president, the Webb, in a sense, is humanity's telescope. Firstly, scientists from all over the world can propose to test their ideas about the physics of the universe using this and, in fact, all other NASA telescopes. And secondly, many of the images will be available starting right away for anyone to download and investigate and use. And NASA invests very heavily into making those data products user-friendly and also invests heavily in tools for citizens at large to be able to analyze them. So this is all knowledge of the cosmos that upholds our common humanity. Biden did not fail to emphasize this togetherness aspect. From India, Professor Jessie Jose from ISER Tirupati is going to peer at her favorite things in the sky with the James Webb Telescope, as is Professor Manoj Puravankara from TIFR Mumbai. And that's Manoj as seen in the infrared. Thank you.